Hey everyone, this video is going to cover the overall lecture for analysis of variance, which stands for ANOVA. In this video I'm going to cover sort of a lecture about ANOVAs, and then as you can look through my feed you'll find examples of each one of the types of ANOVAs that we'll discuss here. So getting started, what is an ANOVA? Well, ANOVA stands for Analysis of Variance, but what does that do for us more than our previous discussion on t-tests and correlations? And so it allows us to work with one or more independent variables. So with a t-test we can only use one IV. With ANOVA we can use multiple IVs. And that allows us to manipulate the difference between levels and conditions. And so we can do that using groups or measurements, so we can treat this as between subjects or repeated measures. And we'll get into this distinction in a minute. It allows us to analyze the differences in means between groups, measurements, conditions, however you want to think about this. But we're still working with continuous dependent data. So most of the work in this semester, we're going to be using a continuous DV or multiple continuous DVs. So we can use t-tests to analyze two groups or two time measurements from the same people. So that's an independent, dependent t-test. However, if you want more than two groups, you have to start doing some extra work. So let's say we have three groups. We'll have to compare 1 to 2, 1 to 3, and 2 to 3, which is now 3 t-tests. If we have 4 groups, it ends up being 6 t-tests, and that increases almost exponentially as you add more groups. So when you do that, you increase the chance of a type 1 error. And remember that type 1 is when you reject the null hypothesis saying you shouldn't. And so it essentially has more room for you to find significant differences that maybe aren't there. So with each additional t-test, we add to our type 1 error. So ANOVA allows us to cover all of those t-tests at once and reduce that chance of error. However, ANOVAs add this additional layer or an extra step to the analysis, which we'll talk about as post hoc tests. So that has advantages and disadvantages, and generally the advantage is considered handling multiple IVs and controlling for type 1 error, and the disadvantages are a little more work. So parts of ANOVA here, which we've got our independent variable, our IV, and in this type of design that has to be dichotomous. So when you start working with continuous IVs, that's when we get into regression. And I don't mean dichotomous here as only two. Here, really that should say categorical. So each group has to be a separate thing. So we can put people based in groups on any category or any kind of experimental manipulation we're interested in. So we might split by gender, or we might give one group some instructions and another group we just let them do whatever they want. So here you have control over the categories, but it has to be some sort of this or that, which is what I mean by dichotomous. Our dependent variable here needs to be continuous. And so generally this is sort of interval or ratio data. Or we might switch analysis types like log regression. So if we have categorical outcome, that would be the log regression section. Or if we have two categorical variables, that would be chi-square. So our DV should be the measurement we had in our study and the things that we're expecting to see change in based on our groups. So coming back to levels versus conditions. So when we start to use multiple IVs, we now need to make a distinction between what we mean by group. Group is a global term that implies each individual cell or each individual mean, but once we start to have more than one IV, group becomes a tricky term that isn't clear enough. So we're going to say that levels are the different groups within an IV, and the conditions are combinations of levels for multiple IVs. So when you hear level, you can know that it's talking about one IV at a time. And when you hear condition, you're talking about both IVs or 3 IVs at a time. So let's give you an example. So an IV might be gender, right? The levels here would be male and female. Now there are no conditions because I only have one IV. But let's throw in 2 IVs. So we've got gender and we've got handedness. So for gender, I have 2 levels, male and female. For handedness, I have 2 levels, left and right. But now for conditions, I'm going to combine those. So we essentially multiply them together. So I have male left, male right, female left, female right. So you can think about this as kind of a square where I have each IV and then their groups. And then when I cross those groups together, I get our conditions. So remember that levels are 1 IV at a time. Conditions are where both IVs come together. Now sometimes you'll see people print 1-way or 2-way ANOVAs, and you'll see these listed in my notes as well. The term way here just implies the number of IVs. So a 1-way ANOVA has 1 IV, a 2-way ANOVA has 2 IVs, etc. 3-way ANOVA has 3. The problem with using 1-way and 2-way is that's also not very descriptive of what's happening in the ANOVA. So we're going to talk about how to describe these better after we kind of explore more of the types of ANOVAs here. So I can talk about a between subjects ANOVA, sometimes called independent ANOVA, where I have all participants are in each level individually. So where I'm only in one level or one condition. So if you think back to my gender handedness example, I can only be in one of those cells. So that would be a between subjects design. I am female and I'm left-handed. A repeated measures design, sometimes called a dependent design or within subjects design, is when I have participants in all of the conditions. So let's say we gave you 4 different exams across 2 classes. So you're in both classes and all the exams. Hopefully you took all the exams. And that would be a completely repeated design, sometimes called a doubly repeated design. So repeated measures here just means that everybody takes every level or condition. A mixed design is how it sounds, it's one of each. So it's where you have one between subjects variable and one repeated measures variable or more. So it's when we take these 2 together, mix and match them. So back to how do I describe ANOVA the best way? So if you have 2 or more ways, so 1-way, 2-way, 3-way, 4-way, so if it's a 1-way design, you can just say a between subjects ANOVA, because that tells me that it's between subjects only. If you have a multi-way design, so 2 or more, we're going to use this kind of number by number denotation. So you might say 2x4 or 2x3 ANOVA, and that tells me the number of levels when you have multiple IVs in like a 2-way design. We're going to combine that with the terms between subjects, repeated measures, or mixed to get a completely descriptive point on what type of ANOVA this is. So let me give you an example. If I said I had a 2x4 between subjects ANOVA, what I would be telling you is I have 2 variables, so 2 and 4 indicates that there's 2 of them. Those variables are both between subjects because I said between subjects only there. One of those variables has 2 levels, another variable has 4 levels, and together, if I multiply them, I have 8 different conditions. So I have 8 different conditions, and every single condition is a different group of people because it's between subjects. If I said I had a 2x2x3 mixed ANOVA, I'm saying I have 3 variables because I have 3 numbers. Some of them are repeated, some of them are between subjects. I'd have to look at maybe the method section to figure out which. One variable has 2 levels, another variable has 2 levels, the third variable has 3 levels, and if I multiply all that together, 2 times 2 times 3 is 12 different groups. Now these aren't all totally separate people. If I said I had a mixed design, I'd have to figure out how many different sets of people there were based on which variable was between and which variable was repeated. Okay. So if we now switch to the process of ANOVA. Okay, so we've described ANOVA. Now how does ANOVA work? If we think about traditional null hypothesis testing, what happens is we set up these 2 opposing ideas. And the null hypothesis tells me that either the level or the conditions, kind of depends on which type of ANOVA we're doing, those means are not different. They're all the same. So every group has the same outcome. My research hypothesis, however, is that level and condition means are different. But that's it. So notice that that doesn't really tell you where those group differences are, just that the groups are different. So if that overall test, sometimes the overall test is called the omnibus test. If you run that and get a significant result, then you have to go on to post hoc tests. And those post hoc tests are like the second layer. And that'll help us determine how groups are different. So I think about ANOVA as kind of like the police. Their first job is to determine if something happened. If something happened, then they investigate where, what, we think about it as a game of Clue, what the crime was. And that allows me to, essentially move on. If nothing happened, then I don't need to run a bunch of t-tests. If something happened, I'm going to investigate where that something happened was. So post hoc tests sort of depends on a lot of different factors here, but this is kind of global lecture. Depending on that type of test, we're going to have to run some other tests, some post hoc tests, to determine how those are different. And usually we do that by doing pairwise testing. Pairwise testing is like Noah's Ark of testing. It's 2 at a time. So group 1 versus group 2, group 1 versus group 3, group 1 versus group 4. So you'll pair them up together to examine which groups are different from each other. There are a couple of types of post hoc tests. A priori tests, sometimes called planned comparisons, means that you planned out which tests you were going to run before you started the experiment. So I know I'm going to compare group 1 to 2 and 1 to 3, and I don't really care about 2 versus 3. A posteriori is all comparisons, and so kind of after the fact, you're like, let's just do all of them. Now for a priori test, you could decide to do all of them, but when you do all of them, people tend to think of them as a posteriori tests. And those are the ones we're going to discuss really because they're the most common. So we're not going to get into contrast comparisons, although those are another option. We're mostly going to focus on traditional pairwise every combination tests. So something to get straight, and especially because I like to quiz people about this, is the difference between a post hoc test and a post hoc correction. So the post hoc test is the actual math that's happening in the background to determine those group differences. That must match the type of analysis you're doing. Now, if you're using R, this is especially important because you can screw this up really easily. It's one little true-false distinction, much like t-tests, where you did paired equals true or paired equals false. If you're using JASP, it's a little less difficult. You can still do it wrong, but it's a little less hard to screw up. So just be sure you put a big star here. So for between subjects ANOVAs, you're going to do, or between subjects IVs. So anytime you have independent variables, different groups of people, you'll do an independent t-test. For repeated measures IVs, we'll do a dependent t-test. So those are tied together because they're the same type of research design. So the math is controlling for the correlated error. So it's controlling for the fact that there are different groups of people or the same group of people. The post hoc correction, which is a separate thing, is an issue. So I started this lecture by telling you that we shouldn't do just a bunch of t-tests because when you do a bunch of t-tests, you create type 1 error. However, once we get into post hoc corrections, that's what we're doing is a bunch of t-tests. You're like, why do this stupid ANOVA thing when I'm essentially doing the t-tests anyway? So we're still going to have to deal with type 1 error problems. So if we're going to run all of those pairwise combinations, or any time you have a lot of tests, we're going to have to control for type 1 error. And that is control can be based on the type of test we're running, or we can pick one of the global options that are available to us. All right, so what are the purpose of corrections? Well, corrections correct. So they control type 1 error by making it harder for you to find a significant difference. So it makes it harder for you to cheat effectively. And the way they do that is by changing the cutoff score required. So we've talked a lot about like there's a certain spot at which you must get to for something to be significant. Often talked about kind of as a race. And what it does is it automatically recalculates our p-values based on the new finish line. And so with this new finish line, our probability scores change. That auto recalculation is actually a really good thing for you because it makes it easy to remember. So this is the big important rule. Remember, you want to use p less than 0.05 as your hypothesis testing criterion. And so we can stick with using that rule because the programs we're going to use automatically adjust our p-values for us. There are lots of different types of corrections. There are entire books on these. What we're going to do, if you're using R, we're going to pick Bonferroni because it's one of the easier built-in ones to pairwise t-test. If you are using JASP, you can use Bonferroni or Tukey. Tukey is a little bit more popular because it's a little less restrictive than Bonferroni, so it doesn't correct quite so much. But it's not very easy to do in R. So both of them are acceptable and they work great. So it just kind of depends on your favorite alphabet soup and your program that you're using. All right, so kind of a switch here as to we've kind of talked about the process of ANOVA now. What is ANOVA doing? So a little bit on the math in the background. No formulas, just conceptual understanding of what's happening when you run an F test. So we're introducing a new distribution and a new letter, F. So we discussed previously Z normal distributions for Z scores and T distributions for samples with unknown variances. And so those are related to our F distribution. What we had before was Z is the standard normal. It's the one that like IQ tests are based on and GRE scores, those sorts of things. Where we know the population mean and standard deviation. Then we talked about T, where we don't necessarily know those numbers. And so T looks a lot like Z if you have at least 100 people. So the T distribution sort of transforms into Z if we have enough people. Now if you take that T distribution and square it, you get F. So all these things are interrelated to each other. So as we move from one statistic to the next, I'm hoping you'll see the connection between them because it's not compartmentalized like this is ANOVA, end of story. The math for ANOVA and the math for regression are the same underlying thing. It's just different instances of the use of the math. And the distributions that we use to help test our hypotheses are all related to each other. Okay, so remember that T is a form of Z that depends on the number of people, and F is T squared. Okay. So there are no negative cutoff scores, so there are no negative F values. If you manage to get a negative F value, you have mega borked the program that's working because all of this is based on variances, and all of that is squared, so there should be no negative values. When we were looking at the T distribution, we had 1 degree of freedom that we sort of used to look up cutoff scores. This was n-1 normally, and that's how we reported in our results sections. However, with F, we're going to have 2 degrees of freedom. One is for our model, or our numerator F, or sometimes thought of as like the number of groups, and then our error term, or the denominator F, which is based on the number of people in each group. So now we're dealing with maybe multiple IVs, so we have to kind of work with multiple groups, more than 2 essentially for T, was how T worked, and the number of people in those groups. Before, we didn't have to mess with the number of groups because in a t-test we only have 2. So that sort of always makes the numerator 2 minus 1. Now we might have 4 groups, so we have to deal with that differently than we did with T. So it's just some examples of what the F distribution looks like. It kind of looks like chi-square. They're also related. But as you add more people, the distribution tends, and more groups, tends to shift to the right. But one thing I want you to notice here is it tends to hover over 1. So we're going to talk in a minute about what is F. And so keep that in mind as we go. So the F ratio is a ratio of between groups variance to within groups variance. And I really hate these terms because that is very confusing since we've talked about between groups designs or between subjects designs and within groups designs or repeated measures designs. So to keep this straight, a between subjects design is a type of ANOVA. Each person is in a different group. Repeated measures designs is a different type of ANOVA where each person's in all of the groups. When we talk about between groups variance, what we're getting at is the differences in means between groups. So the blue lines here represent each distribution. So it represents each group and their mean. So the up and down lines here are the means for each individual group. Okay? What I mean by between groups variance are the red lines. So it's a measure of how far apart my means are. So we kind of find the middle, or the grand mean, and subtract each mean from the middle to see how different they are. So this is like creating a measure of how far apart the means are, because that's what we want. We want those means to be far apart. The orange lines here are the within groups variance. This is standard deviation. So it's how much each group varies within their own little group. So you can kind of think about this as politics, right? So how different is each political party if we manage to have more than two of them, right? And that would be between groups variance. How different are they on their views on taxes, right? But within each little group, so there are factions within each group, you're going to get differences just because people are different. And so that's the orange measure here, is how much people differ within their own group. And that tends to be considered error because we don't know why people are different within their own group. We want to know why they're different across groups, but within the groups, I just don't know. Okay. And so I'm going to call the between groups variance model variance, or the numerator variance. And that was the red one on the picture. And it's the average difference between levels or conditions, kind of depending on if you're doing a one-way or two-way design. Okay. I want that score to be really large. And that score being large implies that my experiment had an effect. So we want big differences between groups. If the numbers are really small, that indicates that the means are not very different between groups. And large differences indicate that those means are different. The error variance, or what in the original picture was labeled within groups variance, and that's noted in orangish yellow on that picture. That's an average of within group variances. We want that number to be really small because that means that we measured our groups with a lot of precision and their scores don't vary widely. So the mean represents that group really well because everyone's very close to it. Large numbers indicate that there's a lot of error, or there's a wide range of scores, and so using one mean number to represent that entire group is not very good. So a large spread means people vary a lot. Small numbers for your error term means that scores pretty much tightly cluster around the means. Sometimes you'll hear people call this sort of thing individual differences. So people are different within their own groups, and we don't necessarily know why, so it's our error term here. So when you see an F ratio reported, you'll get your model degrees of freedom, sometimes a numerator. Right? And so it's the number of levels or conditions minus 1. So it's the number of means, so if we had 3 groups, minus 1. The error degrees of freedom, or the denominator, is the number of participants in each group minus 1, plus second group minus 1, plus second group minus 1. And I'm not going to really quiz you on this so much as I want you to get that it's n minus 1, and that's going to keep reappearing throughout the semester. So it's n minus 1, n minus 1, n minus 1. Okay. If we look at effect size for F tests, we're going to use eta squared. Eta squared is a measure of the relationship between the amount of variance accounted for by our group variance, right? That was our model variance of the number we wanted to be really big, to the total variance. So it's a proportion of variance accounted for by your model. So it's how much we are explaining by adding this independent variable to our understanding. Now eta, since it's a proportion, ranges from 0 to 1. And we're going to use 0.01, 0.09, and 0.25 as our small, medium, and large criteria. You'll see different numbers here depending on which book or person you're reading. I got these numbers from the correlation numbers. So if you remember way back from the correlation lecture, we did 0.1, 0.3, and 0.5. If you square those, it's 0.01, 0.09, and 0.25. Okay. R and eta squared are intrinsically tied. They're related to each other. Okay. The interpretation of this is how much variance is due to that IV and not due to error. So we want bigger numbers. But we're dealing with people here. At least our psych people are, right? And so 9% of variance might be a lot. 10% of people's behavior being explainable is kind of a lot. If you're using R, this output will be listed as GES for generalized effect size. The formula changes depending on the type of design, so you can list this as eta or GES because that's the numbers that we're using here. Okay. For power, what we're going to talk about, we're going to use is G-Power. G-Power is a fantastic program. It is free. If you just Google G-Power, you'll find it to download. And for each of these types of ANOVA, we're going to talk about how to calculate power. On Blackboard, in my course, there is a chart that explains all of the designs we're going to use this semester and how to fill in G-Power for that type of design. So be sure you hang on to that thing to help you calculate power for your assignments. So getting into more of the, what do I do with ANOVA? We're going to screen accuracy the same way we've been screening. You want to make sure their dependent variable and their groups are listed correctly. For missing, there's only one DV, and there's not a whole lot you can do about filling it in, because then you're making up an entire participant. So unless you have 27 repeated measures levels, and if you do, good God, why, right? You're probably going to have to drop people who are missing any data, because we don't want to make up their data points. Outliers, we've talked about Mahalanobis or z-scores for my JAS people, but for that to run, you have to have more than one continuous variable. So pretty much everybody's got to use z-scores at this point because we are using one DV. Okay, so for every between subjects design, we're going to use z-scores. If you are working in R for repeated measures designs, you can use Mahalanobis distance, but a lot of this is going to focus on z-score elimination. With between subjects designs, there's only one DV, so there's no additivity to check for. With a repeated measures design, there's a new rule. Basically, R cannot be 1. Okay, it has to be less than 999, which essentially means R can't be 1. Now, with repeated measures, I expect people's scores to be correlated, and if they aren't, you tend to lose power. But we expect them to be correlated because they're the same freaking people over and over and over again. Why is the score different? Well, when we expect them to be that correlated, it's kind of the purpose of the study usually. Essentially, R cannot be 1 or the whole thing mathematically will not run. So here you'll just check to make sure that the two levels are not perfectly correlated or it won't run. Okay. Do your normal normality screening, your normal linearity screening. Homogeneity and homoscedasticity, you can use a residual scatter plot to screen. But once we get into doing each one of these tests in your specific program, we're going to talk about Levines and sporicities, the sporicity assumption, which we're going to use Mockley's test. So I'm not going to go into those here. I'm going to get into those with the tests that they matter for, but there are tests for homogeneity specific to between subjects and repeated measures designs separately. For our examples, what we're going to do is we're going to do one way between subjects and one way repeated measures. Those are required for people in my course. There's two-way between subjects and two-way repeated measures examples that are suggested for our JASP users. And everybody's got to do a two-way mixed design. So we're actually going to work through 5 different types of these designs. If you're just watching these videos on my YouTube channel, you'll be able to find all of these in JASP and in R, so you can calculate these different tests. And for each one of those, we're going to talk about power using G-Power, how to do data screening, how to run the actual ANOVA part, post hoc tests and effect sizes for those post hoc tests, which if you're using JASP, but there's brand new effect sizes for post hoc tests for like one way between subjects and multiple way designs, which is really fantastic. That's new. And then for graphs, how to make a graph of the design, and then how to write those up. And so this concludes our lecture on ANOVA, and then we'll move into examples next.